Let's move on to some of the more advanced topics in vectors. First of all, the notion of linear independence of vectors. That is an important one. Not just important, actually a critical one. In the last example, in the last video, we had a red vector and the blue vector. They were both in R2, and we saw that we could get to all possible vectors in R2 because these two vectors are actually linearly independent. We haven't defined what that means, but we will do that in a second. But the statement that we will make regarding that is that using x1 and x2, we can span all of R2. I'm going to call that the vector space of R2, but that's not very critical right now. Now let me give you the condition for linear independence of vectors in R2 after having defined linear combination, which is just a new vector, take the first vector, scale it by some number, take the second vector, scale it by some other number, and that is my green linear combination. And then the condition for linear independence is that if you cannot create a linear combination that is equal to 0 without S1 and S2 being 0, then X1 and X2 are linearly independent. This statement is a bit hard to digest, but we will get used to it. Then there is a second statement that says that if I have two vectors that are linearly independent in R2, like this, my red and blue vectors, then I can create any vector y in R2, and the linear combination that equals y will be such that there's only one set of S1 and S2 that will give you that linear combination. In other words, linear combinations are unique. So it can be proven both algebraically and by construction. I prefer to give you a construction kind of proof, a proof by geometric construction. So let's do that first. Suppose I have some random green vector that I'm looking at. So it looks like -2, 3.6 or something like that. And my original vectors, the linearly independent ones, my red vector is 1, 2, and my blue vector is 3, 1. Out of these, I want to create some linear combination so that I get the green vector, and at the same time, I'm hoping to see that there's only one way in which I can do this. What I'll do is to draw a line parallel to x2 through the tip of y, meaning I'll draw a line on top of my x2, move it to the tip of y, and then I'll extend my red vector to hit that line. So I'll draw a dotted line that move it to the tip of y and extend my red vector to that line. Now I have hit the blue dotted line with my red vector, and the second thing I would do is to do the same thing with my red vector. So that means I'll draw a red dotted line along my x1, then move it to the tip of y, then extend my blue vector to that line. Now can you see that y is actually the sum of this vector x1 prime that I extended to the blue dotted line and my x2 prime that I extended to the red dotted line? It is because what you see here, this guy is a parallelogram and this is a diagonal, and as you know by construction, the diagonal of the parallelogram created by the vectors being the adjacent sides will give you the sum. So y now is actually x1 prime plus x2 prime. Now you can see that x1 prime is on the same line as x1. So it's a scaled version of x1. We know that scalar multiplication works that way. How would you find that scalar multiple? The scalar factor, you would take the norm, the size of x1 prime, divided by the size of x1. That will give me the scaling factor that I need to multiply my original x1 so that I can get x1 prime. So length of x1 prime divided by length of x1. Similarly, I'll take the length of x2 prime divided by the length of x2 to get the scaling factor for my x2 prime with a slight modification. Now that it's in the opposite direction, I have to take the negative sign. If it is in the same direction, I will take a positive sign. In other words, I'm actually doing a length but a signed length. The length here is a sine length. Is positive if it is in the same direction, negative if it is in the opposite direction. After having done that, I can see immediately that y is s1 times x1, because s1 times x1 is my bright red vector x1 prime, s2 times x2, that is my bright blue vector x2 prime, and the sum is actually y. So that's that. And this also has a visualization, so let's take a look at that one. So the idea here is that I can move my y anywhere, and then you can see that my blue dotted line is parallel to my vector here, and my red dotted line, which hasn't actually moved to the tip here. But if you move that line through the tip of y, then you can find x2 prime. The thing is that you can actually change the vectors, and the construction will change like that. And then there is one point at which it suddenly becomes impossible to do this, and that is the situation of linear dependence, which we will see in the next slide. So linearly dependent vectors now. The question is it always possible to span the space by any two vectors x1 and x2? I kind of tipped my hand here and I showed you that it couldn't be done. The situation where it cannot be done is when the vectors are actually linearly dependent. So we need linear independence of the vectors so that they can span R2. Now let's take two vectors now. X1 is 1.5 and half. X2 is 3 and 1. Can you say anything special about these two vectors? These two vectors are actually linearly dependent because 3 is 2 times 1.5, 1 is 2 times 0.5, so they are in the same direction. So let's start making all possible linear combinations. S1 times red vector, S2 times the blue vector. Keep doing that. What's the set of all possible green vectors that are the linear combinations? It'll turn out that it's a line of vectors. The line is defined by either the red vector or blue vector because they are on the same line. So let's see that here. So my red vector and blue vector, they are on the same line because red vector is kind of like half of my blue vector. Then I scale the red guy by something and blue guy by something, and I get a point. Some other scaling factors, I get another point, and I keep doing it. I get different points. Then after doing that for some time, if you look at the points, they form a line. That is the green line there. They are on the same line. Saying it differently, the sum vector, the green vector, always falls on the same line as the red vector or the blue vector, or the red vector and blue vector together, they span only one line, not all of R2, but only one line of vectors. So the reason why we couldn't get to all vectors in R2 is that these vectors were linearly dependent. There was no way, no scaling factor that will let us get out of that green line. Later we will call this a vector subspace of R2. Remember, the condition for linear independence was that you should not have a non-trivial linear combination of these two vectors that will give you the zero vector. Now we know that x2 is 2 times x1, so 2 times x1 minus x2 will have to be 0 because 2 times x1 is actually x2. So subtract it, you'll get 0. So that is a linear combination of x1 and x2, and the coefficients are not all 0. The coefficients are not trivial. So a non-trivial linear combination giving you the 0 vector, that means the vectors are linearly dependent. When they are linearly dependent, they are defining the same line, and all the vectors that you get by taking linear combinations will be on one line. Or, in other words, if you take a vector that is not on the line and try to form linear combinations of these vectors to get to that vector as a sum, you will never be able to do that. You cannot get out of this line. You're kind of confined to that line. One more thing, if you take a vector that is actually on the line and then try to form linear combinations of x1 and x2 to get that vector that you have taken, which is on the line, then you will see that you have an infinite set of possibilities. You can find an infinite set of numbers s1 and s2 such that that particular vector on that line can be expressed as a linear combination of the red x1 and the blue x2. So let's try doing this once more. This time my original two vectors, x1 1.5 half, x2 3 and 1, linearly dependent because x2 is 2 times x1, and I'm going to try to do my construction, which was to draw a line parallel to my blue vector and take it to the tip of y and extend my red vector so that I can hit this line. Now I can sit here and extend my red vector till the end of time, but it will never hit my blue dotted line because the blue dotted line is parallel to the red one. Similarly, if I take my red vector, draw a line, the red dotted line, take it to the tip of y and try to extend my blue vector, again, that is not going to hit the red dotted line because it is parallel to the blue vector. So there is no way in which I can actually geometrically construct a linear combination. So one question here, can you have three linearly independent vectors in R2? The answer is no. And how many linearly independent vectors are there in R2? The answer is 2. You cannot have more than 2 because, as you saw in the previous question, if you have 3, you can always find a linear combination that will give you the third vector. In fact, it is kind of obvious. I use the same color codes. This was my x1, this was my x2. They are linearly independent. And x3 here in green, that is my y. We saw that any given y, you can always do this geometric construction so that I can get y as a linear combination of those two. Then that particular linear combination minus y is going to be 0, minus y is minus x3 here. So that is not a non-trivial linear combination because s1 is not 0, s2 is not 0, and s3 is minus 1. Think about it. And for that reason, there are only 2 linearly independent vectors in R2. Now let's just try to extend it. What do you think the situation is in R3? It is going to be 3. You can find 3 linearly independent vectors in R3 and no more. In Rn, n. Those things are a bit harder to visualize because it's not a line that you have to draw through the tip of one vector, the more complicated planes in the construction. But you will develop those intuitions soon. How many linearly independent vectors are needed to span R2? 2. About R3? 3. About Rn? N. Now there is a new operation that I want to talk about. This is a vector dot product. It is also called the inner product or the scalar product. It's not scalar multiplication, it's a scalar product. We will almost always use a dot product in this course. So let's take an example. My red vector now is 5, 4. Blue vector is 3, 1. The definition of x1 dot x2 is basically multiplying the corresponding elements and then accumulating it. It's a sum product. So 4 times 3, 4 times 3 plus 5 times 1, which turns out to be 17. In Rn, same idea. It's the first element of the first vector times the first element of the second vector, second element of the first vector times the second element of the second vector, and so on. It's a sum product. Sum them up. So it's a sum running from 1 to n because we are in Rn. And take the first vector, take the ith element, take the second vector, take the ith element, take the product, and then sum them up. That's the definition. Now there's one more thing. We touched upon it a couple of times. The length of a vector or the size of the vector. We will use the word norm. That is the standard way of saying it. And we will use the symbol double vertical bars. And we're going to say that it is equal to the sum of the squares of the element square rooted. Now you can think of this as a dot product of x with itself because then it will be x1 times x1 plus x2 times x2, etc. And then you just take the square root. After having defined the dot product, you can just write x dot x and then take the square root, and that is the norm. In other words, the dot product is the square of the norm. One thing to note is that norm is defined to be positive. If you scale the vector by some scalar s, then s will get in each one of them as a square. Then you can pull it out, but you get the absolute value because square root is wholly positive. So the norm will scale by the absolute value of the scaling factor, which is kind of neat because when you scale a vector, you expect its size to scale like that. Then there's this idea of a unit vector, which is a normalized version of the vector. You take the vector, divide it by its norm, then you get a unit vector because after that, you take the norm of this guy, that is going to be just 1. And you will use the hat notation. So x hat is x divided by the norm of x. And you can think of x hat as though it's defining a direction or a line in the coordinate space. So x hat defines a direction. What's its norm? It has to be 1 because it's a unit vector. You just took out the norm right there. Now let's look at the norm using a visual here. You take the vector 3, 4 and take the norm. So x dot x will be 3 times 3 plus 4 times 4, that is 25. Square root of that is going to be 5. So x hat is a fifth of that vector, which turns out to be 0.6 and 0.8. So we saw the definition of a dot product using the sum product of the elements, but there's another definition using the angle also. So x1 dot x2 is the norm of x1 times norm of x2 times cosine of the angle between them, which is kind of interesting. And this is actually used in, say, natural language processing, where you have documents as vectors, and the similarity between documents is actually defined as the cosine similarity, which is essentially using this formula. So compute the angle between two documents using this formula, and that would be a measure of the similarity. Now, looking at this formula right here, you can see that the norm of x2 times cosine theta is x1 dot x2 divided by the norm of x1. And now what's x1 divided by norm of x1? That is a unit vector along the direction x1. And what's x2 cosine theta? If you think about the right angle triangle there, then that is the projection of x2 in the direction along the line defined by x1. So that is a projection. Think of the case where x2 is orthogonal or perpendicular to x1, then the projection is 0 because cosine of theta is 0 when theta is 90 degrees. Now you have two definitions of dot products. This one, the sum product, and this guy, and they are the same. At least in R2 you can see that they are the same, but are they the same in general in n dimensions? They are. And you can try proving it. Of course, you will need a little bit of trigonometry here because you have cosine theta there, but it can be done, and there is an example proof there using the law of cosines. So try going through that. Now let's take a look at visualization. I have two vectors there, and they are carefully chosen so that the angle between them is actually 60 degrees, and the norm of each one of them is 5. 3 and 4, easy to see. 3 square, 9 plus 4 square, 16. 9 plus 16, 25, square root 5. So it's the same here also. Let's take the dot product using angles. So it's going to be 5 times 5 times cosine of 60 degrees, which is half. So you get 12 and a half. And by the element by element multiplication, you will get the same thing. Obviously, you have to, because there's only one mathematical truth. And now the projection of x2 onto x1, that is going to be 2.5. It doesn't really quite look like 2.5 in my picture here because it's not drawn to scale. My grids are not square but rectangular. Let's look at online visualization that I've created for you. There, you can see that the projection is actually half of the length of the red one. And if you move it around, you can see different projections and different angles. And if it is 90 degrees, you can see that the projection becomes 0 there. So just to play with it, interactivity is good. Just one more thing in this advanced topics for vectors that I want to go through. We defined the Euclidean norm, the 2 norm using the squares and sum of squares and square roots. Let's define something called the P norm. The norm that we have defined, this is the norm of x. These are the components of x. Square them, sum them up, take the square root, and that's the way we define the norm. And that's actually the Euclidean norm based on the Pythagoras theorem and all that. But there's a general definition of norm, just extending, replacing 2 by p. Of course, since p is any number, you have to use absolute value of the components, not just components as they are. And then you would take the pth root. So p norm of x is take each element of x, take its absolute value, raise it to the power of p, sum them up, and then take the pth root. This is called the p norm. The Euclidean norm, of course, is 2 norm when p equal to 2. Then there are interesting norms there called the Manhattan norm, which is when p equal to 1. This is also called the city block norm. When the blocks are laid out as squares in a grid, in order to reach from one point to another point, you have to go horizontally and then vertically. And you can take any kind of zigzag path, but they will all add up to the same length. That is a Manhattan norm. It's also called the taxi cab norm for that reason. Take a look at that one. P equal to 2 is like the line of sight kind of distance. That is a Euclidean norm, and that's the one that we use most of the time. Then when P equal to infinity, that is called the infinity norm, and that turns out to be the maximum value. I will ask you to prove this on your own. Well, I'm sure you will be able to do this. Just let P tend to infinity in this expression, and then you will see that it's actually going to pick out the largest value of the component, even when the components are repeated. So try proving it. Now we are done with vectors now. We will be moving on to matrices in the next video.